So in this video, what we'll see is we'll see the scaling laws again, but keep in mind that the scaling law of electrostatic principle that we saw that there is the considerable reduction in the electrostatic forces. There was a 100 times reduction when there was a scale of reduction scale of 10. So we'll see what happens in the electromagnetic forces, but keep in mind that in the macro scale devices, we mostly use electromagnetic principle for actuation, as in our motors and such. So we use electromagnetic principle to as the main principle behind motor, right? So what we'll do is we'll see how electromagnetic principle holds up in the scaling factor, and then see what happens to the scaling factor when we miniaturize it by, let's say, halving it, or when we do it by a factor of 10, what happens to electrostatic principle and electromagnetic principle, and from that we'll conclude which one is the better suitable for MEMS devices. Fine. So we'll just summarize that the when there is a 10 times reduction in the dimensions, there is a 1,000 times reduction in the potential energy when we use electrostatic forces, and when we use electrostatic principle, and when we go and look upon the electrostatic forces, there is a 100 times reduction in the magnitude of electrostatic forces. We will move on to the electromagnetic forces. What is electromagnetic force? Electromagnetic force is the force generated when conducting wire is passed through an electric current. It is subject to an EMF when it is exposed to magnetic field with a flux B, and you can see the illustration over here. So as per Faraday's law, we can find that F is directly proportional to L power 4. So since L is our length constant, we'll put as L equal to L. Since L is L power 4, we'll conclude it as linear dimensions power 4. Okay. So when the scale, as per the scaling laws, when the dimension is reduced by half, what would be the change? So when the dimension is reduced by half, you can see that f becomes 2 power 4 equal to 16 times. So whereas the reduction of when the dimensions are reduced by half, the electromagnetic force is reduced by 16 times. But when it is applied to electrostatic force, as in the dimensions are reduced by half, the electrostatic forces, they reduce only by a factor of 4 times, as in 2 power 2, it becomes just 4 times. So we can conclude that when we look up both upon the electromagnetic and electrostatic forces, the electrostatic forces, they do not reduce as much as compared to electromagnetic forces. The electrostatic forces, there is a slight decrease in that, as well as when you look upon electromagnetic force, there is a significant drop in the electromagnetic force. So that is why in MEMS and microsystems, mostly for actuation, they use electrostatic forces instead of electromagnetic forces. This is an important point which will be the key to find out what sort of actuation method you are going to use for your MEMS system.
Virtually every vehicle made within the last 20 years contains an astonishing piece of technology that remains dormant, sometimes going unnoticed for years, until the unthinkable happens. When an airbag deploys, the electronics of the airbag system take just 15 milliseconds to decide if the forces on the vehicle are severe enough. Within 60 milliseconds from the instant of impact, the airbag is fully deployed. The entire process from initial vehicle contact to deployment happens at twice the speed of a blink of an eye. And at the heart of an airbag system is the same technology that allows our smartphones to detect motion, inkjet printers to print, and projectors to throw an image on a screen. These technologies all rely on the emerging field of microelectromechanical systems. Sensors was directly responsible for the success of MEMS technology and micromachining technology in the industry. With over 500 million of these devices in vehicle operation today, the reliability of the technology has been proven. Some vehicles even employ dozens of MEMS accelerometers for their traction control, braking, and handling aids. MEMS-based accelerometers can even be configured to sense motion in 3 axes. With the rise of smartphones, this capability quickly became indispensable. In this configuration, the proof mass is suspended at the center of a frame by microscopic springs in a manner similar to a trampoline. Acceleration in the XY plane is sensed by capacitive fingers fixed to the frame of each respective axis, similar to a single-axis accelerometer sensor. Both sensing structures also contain electrodes that can sense vertical travel of the proof mass, forming the simultaneous action of a z-axis accelerometer. Accelerometers are not just limited to automotive and mobile phone applications. They can also be found in earthquake detection equipment, VR gaming systems, pacemakers,